So if a document contains arachnocentric, then it's very likely to be relevant to the query arachnocentric. So we want a high weight for arachnocentric. But then, again, frequent terms are less informative than rare terms. So have something like high, increased line, or a query that is the. So a document that contains these terms is not more likely to be relevant than a document that doesn't contain these terms, because they're like sort of spurious matches, and it's very rare. It's very infrequent that you put that in the query and you expect that to be an important signal for determining relevance. So the key intuition is that you use the document frequency, the number of times you see the term in the collection, to capture this signal, right? That a rare term has more discriminative power than a frequent term. So this is it, right? So df is the document frequency, the number of documents that contain the term. So essentially, you want the inverse document frequency. You want this expression here, n is the total number of documents in the collection, so you want n divided by the document frequency, and you soften it with the logarithm. Right? So something that occurs in every document, not good. Something that occurs in just one document, very good. Right? You want to have a higher score here. Logs are great for a number of things, but essentially if you get it wrong, logs only care about orders of magnitude. It just cares about the number of zeros that you have, right, in this ratio here. So if you get it wrong by a couple of numbers, instead of 2, 5, it's not going to matter that much because the log is going to take care of it. So that's why the logs are great. Of course, IDF doesn't have any effect on one-term queries. Right? It only affects when you have multiple terms in the query, right? Because the contribution of IDF is going to be the same. And this is the intuition. You have a query that is capricious person, so IDF weighting makes the occurrences of capricious count much more than the occurrences of person, because this is a very rare term and this is a very frequent term. Okay? I'm going very fast, but you already know this process. Now, TF-IDF. Brilliant idea. Multiply TF times IDF, right? So you have the equation for TF we had before, and the equation for IDF we had before. You multiply these two, and that's your score. And this works surprisingly well in a number of occasions. You'll be amazed by the power of this TF-IDF in text representation. Interestingly, you can write it like TF-IDF, and some people confuse the hyphen with a minus sign. So it's not a minus, it's a times. All right. Again, so how you compute the score for a query and a document? So you sum all these TF-IDF scores for all the terms that occur both in the query and the document, and you ignore the rest. This is great, because it means that you don't have to look at all the terms in the document. You just need to know if a particular query term is in the document, which you can do efficiently with an index. And this is where an index is great. It allows us to do sub-second ranking. Now, the next component was the document length. How long is your document? How many words you have? So think about it. If your document is super long, then the probability of having the keywords there is higher. But then maybe it shouldn't be as relevant as a shorter document that is more concise and to the point. So you want to penalize longer documents that match query terms. And this is essentially why the vector space modeling came in. So ideally, you have a huge vector space with a lot of dimensions. Each dimension is one of the terms. So every term in your collection accounts for one of the dimensions in the vector space, the axis. Right? And documents are just vectors in this space, arrows. Right? Which of course, very highly dimensional, and most vectors is very sparse. I mean, most of the components are going to be zero. your vectors are, can be efficiently represented by a sparse structure like an image. So essentially, the first thing somebody said was, just multiply the two vectors, and that's sort of going to work. Just kind of what TF-IDF does, and then sum the occurrences. Now, somebody might think, now you have the vectors. You have here one document, and another document, and another document, and a query. Right? And these are the dimensions. You have these two terms, gossip and yellow. And you might think, well, why don't you take the distance between the vectors? So distances are a very bad thing, because essentially the distance between this query and this document is very large, even though the distribution of the terms is very similar. So you don't want to take the Euclidean distance. You want to normalize the representation of this vector. So essentially, one cool way to do it is to take the cosine of the vectors as your similarity. So the higher this angle is, the bigger this angle is, the more distant the vectors are. And the closer these two vectors are in terms of the angle, then the more similar they are. So in practice, what this implies is that the cosine of an angle is close to 1 if the angle is small, and 0 if vectors are completely orthogonal. And this is the expression. So essentially, dk will be 1 or 0 whether you see the term or not, or the TF-IDF if you want. Component of the vector, and you kind of multiply the components, right, of both vectors. So for terms that occur both in the document and in the query, you multiply these values, and you divide by this expression here, which actually accounts for the length of the document. So in practice, what you're doing is that every count is normalized by the length of the document. Okay? So if you have a very short document, then this number is going to be higher because the denominator here is going to be smaller. All right? So shorter documents, same number of occurrences in shorter documents are going to be much more important than the same number of occurrences in longer documents, which is what we wanted. And this is vector space model ranking, 1970. And essentially, it was difficult to have something that was noticeably better than this for a lot of years. Again, very, very simple. It's a nice metaphor about geometry and how you represent things. So that's why people like it a lot. Now, probabilistic IR. And I don't think I have a lot of time. But anyway, you'll be hearing a lot about probabilities later on in the lectures. But an IR system, what is a probability? Right? So I guess a probability is something different from different people, depending if you're Bayesian or frequentist or whatever. But essentially, you can see a probability as an intrinsic property of a system, right? Something that happens because this system behaves like this, right? You toss a coin and it's 0.5 because that's the number of times you're going to hit heads or a tail in the coin. Another way to see this is if you repeat an event many, many times, right? The limit is going to be the probability. So if you toss a coin 1,000,000 times, then half of the times, on average, you're going to have a heads and half the time you're going to have a tail. But the most interesting interpretation is that probabilities can be beliefs. So they can represent how much you believe in an event to happen. And this is great because you don't need an event to happen many, many times to assign a probability to it. Okay? Which is something that you cannot do with this frequentist counting the number of times that something happened approach. All right, so then our IR system now is going to be made up of random variables. There's going to be a event space, there's going to be a sample space, and our interpretation, our representations of queries and documents and relevance are going to be samples from this event space. Okay? So everything will be a random variable or a distribution for probabilistic IR. And why do we care about probabilities? We care about probabilities because nothing is perfect, not even an IR system. So you want to quantify how imperfect you are. but from some other reason, which is this probability ranking principle, which is very important, by Robertson. And he said, I'm going to read it out. If a reference retrieval system's response to each request is a ranking of the documents in the collection in order of the decreasing probability of relevance to the user who submitted the request, where the probabilities are estimated as accurately as possible on the basis of whatever data we have made available to the system for this purpose, the overall effectiveness of the system to its user will be the best that is obtainable on the basis of those data. Again, very poetic. How do we put it in numbers? Right? And this is the basis for all probabilistic approaches for IR. What is this thing saying? This saying is that if you can estimate the probability of relevance, which is the probability of observing relevance. Relevance, think of it as 0, 1, random variable as 0, 1. Given a document, which we haven't said what it is, and you can estimate this accurately. So you can come up with a number that actually approximates this probability accurately. And you're using all the data that you have. And all the data can be documents, queries, context, users, whatever you have. You have to use everything you have. Then you have the best possible accuracy. Essentially, you have the perfect IR system, the best possible IR system. So that's great. With one caveat, which is that is assuming that relevance is independent on any other document in the collection. So you can measure relevance just by looking at individual documents, which is not generally the case for some applications. But still, again, I'm rushing, but you're working with representations here, right? It doesn't mean that a U here is a user. It doesn't mean that, we're looking at a human being here. So what these variables represent, what these probabilities represent, is whatever is available to the system, whatever chunk of reality you have available in your system, right? Which might be just 2 and 3 keywords, no profile of the user, no context, right? So this is what is going to represent these relevant variables. So it really depends on what the system is seeing. And if you are missing a lot of this information, you can think about this probability of relevance as something that is marginalized over all the possible users, all the possible context, or all the possible profiles of people. Right, so I think Heather is going to talk about Bayes theory, so I'm going to skip this. But for those of you people doing machine learning, essentially this is related to the error rate of the Bayes classifier, right? Which is this is the best error rate you can get. Essentially selecting the class that maximizes the posterior probability, given all the evidence. Now, how do we estimate all this? So very carefully. Now, you're going to have a lot of parameters in your model. You have a lot of these estimates. But I think, for the sake of time, I'm going to flick through. You can request this slide from me if you want later on. These are all ways of estimating. You're lucky. I'm just skipping all the heavy equations because we're running out of time. I can leave them here to freak you out. I have worse ones. But there are like really 2 key probabilistic models of IR. One is BN25, okay, and another one is the language model family. So BN25, for the people who know something about graphical models, essentially says that relevance can be marginalized over this combination of these variables here, which are called eliteness variables, and the number of times you observe term frequencies. So it's like saying, well, if you observe this term this amount of times in this document, it depends on this variable whether these occurrences are spurious or are actually relevant. So it's trying to mix these 2 factors, and it uses 2 Poisson distributions to mix those factors. But what you care about is this interesting formula here. So this is BN25. Tachan. It has 2 parameters, this B parameter and this K parameter, so ignore. This DW is the term frequency, so it's the number of times you see the term. And you see they have this component here, ND divided by N average. So this is the ratio between the document length and the average document length. So essentially, what is this whole thing saying? So it has 3 components. One is the term frequency here. One is the document length, you are divided by the document length, right? The higher the document length, the less the impact of this term here. And you have IDF, which is this thing here. TF, IDF, divided by document length. So slightly more sophisticated way of saying vector space. Okay. This is very effective. This is, in a lot of IR papers, this is considered as the baseline to be. And it has been like that for 20 years or 15 years, surprisingly. A few key intuitions here is that, again, repetition is less important than different query words. So you have a term 10 times, then that's not as important as having 2 terms 5 times. All right, so, okay, language models. And I'm touching upon this because you'll be seeing more about them. But essentially, language models are a generative approach for so it's like a generative explanation of why documents are generated out of the string set, right? So you have a probability distribution over strings of text. You observe words, and every word occurrence has a probability. It's as simple as having like this urn metaphor, right? So if you have a bucket with a lot of balls of different colors, red and blue and yellow and white. So if you draw a random ball, what is the probability of the ball? So super simple, like statistics 101. So instead of balls, you will have words. Instead of the bucket, you're going to have a document where you put this bag of words. It's going to be this urn. So a language model is just this thing here. So you want a probability for this string, so this sequence. Right? The cat sat on the mat. Or the mat sat on the cat. So you think, which one do you think is going to be higher? One. In IR is the same, because you have a bag of words model, so it really doesn't matter how you put the words. Right? So if you have a bag of words representation, you're going to be assigning the same probabilities. For a general language model, if you have unigrams or bigrams or sentences or whatever, so it really depends on what are your events. Okay? Also, you have things that can be mixed languages. You can have language models that combine English and Spanish. And for some applications, you want this probability to be very high, indeed. If you're doing machine translation, for instance, you want this thing to be very likely. Right? Because actually, El Alfombra is on the match, so it's a perfect match. So what is a language model? Well, essentially, you have a model M, which is whatever, we'll see now, and you have an observation S, and you want the probability of getting S through random sampling from M. Right? So it's actually producing the string. So it's a story that tells you how to produce strings out of this model here with some probability. So what you do is, what you assume is that the user thinks of a relevant document and then starts picking some keywords that describe that you use as a query. Right? So this is the underlying thinking of this probability here. So what you do is you get the probability of producing the query from a document. You get this probability of query given the document. And these two are probability distributions. They can be modeled in a variety of ways. We'll see the simplest one. And this is called query likelihood. And the idea is that the probability of a document being relevant is strongly correlated with the probability of a query given a document. Again, same similarity principle. I mean, you use the same words, then you got to be talking about the same thing. You also assume that the user has a reasonable idea of the terms that are likely to appear in the ideal document. Right? And you can distinguish between those. Most of this is blah blah. You really wonder questions. So how do you do this? So this is what you do. Right? You get a query, which is made up of k query terms. You want to estimate the probability of the query given the model M. And essentially, well, you say, well, these are independent events, so you can multiply them. Which is not realistic, but it's what you do. So this is a multinomial story of how you generate this. You can have a multiple Bernoulli explanation. So you can have this probability for, this should be document, and this should be document. I guess this is the most used representation for a language model, a multinomial explanation, right? You just take the query terms individually and you multiply that probability. Now, the problem is that you don't know what M is. You have no idea. So you can have a maximum likelihood estimate. Say, the document, the distribution of terms in the document is going to be the reality. So you count the number of times the query term occurs in the document divided by the total number of terms occurrences, the EARN metaphor. You have all these words in the document, you pick one, and this is this probability here. Now the problem is that here you're doing a multiplication of this PQI given M. What happens if the query term is not in the document? And it can be for many reasons. So essentially this whole thing is zero. So you're going to say, this probability of the query given the document now is zero, because if you have, so say that you're assuming an AND mode style of query. Okay? And that's not desirable. Really that's, we've seen that is very restrictive, so you want to do something that is a sum of some weights over the query terms. And if they don't occur in the document, you want to give them a zero score, but really you don't want to kill the whole game. So this is called the zero probability problem. So what you do is you say, all right, so now I'm going to chop this up into two different parts. So this maximum likelihood probability and a back-off model, which comes from the collection. So this is saying, you put all the collection terms in one big bag, right? All the documents together, all the words go to a big bag, and you pick this word. What is the probability of picking this word, right? So this is this back-off model, and you just linearly interpolate. There's more ways to do this. And this interpolation is also known as smoothing, but this discounting methods is to take values of the probability. So how does it go? Let's see. I'm rushing, but this is it. Again, the score in the language modeling framework with this particular smoothing, there's other types of smoothing, is just you take all the query terms that occur in the document, and you sum some number for each one of those. What you sum is this number here. Right? This number is term frequency times this summation is constant for all the documents, so you don't really care about it. So you have the log of the term frequency. Does it sound familiar? And then you have the document frequency of the term. And this sum here is just the document length, the number of terms in the document. So, and this is the mixing parameter. So you want to give more importance to the numerator or the denominator. So essentially you have mixing parameters, doesn't matter what it means. You're dividing something by the document length, and you have the TF-IDF here. So it's TF-IDF document length again. It's the same thing, slightly different formulation. Right? I'm not being really quick, but it's, the questions are always going to be there on the paper. It's just the intuition of what things are working for modeling. What other things you can do? Well, as I said, you can try to model term dependency, the position. So if terms in the query occur closer in documents or not. This in the language modeling framework is called Markov random fields. It's a paper from 2005. But then you can say, well, if this term matches on the field, on the title field of the web page, then it's possibly a higher indicator of relevance than if it matches on the body of the page. So you want to reweight differently matches depending on which part of the page they occur. These are called fielded models, and the extension to BN25 that takes into account fielded information is called BN25F. And that's basically it. I had this set of crazy slides on a paper that we wrote last year, published on Cigayar last year, which means now you have all this 4 or 5 signals. What if you can come up with a lot of signals, right? So in general, the general answer will be do machine learning, combine them with a machine learning method. Now, if these signals come from the query terms themselves, you are sort of incorporating features, say, into the machine learning model that are dependent on each other. So you really want to engineer these features as well as you can. So essentially, this model is kind of telling you how to model these features. So, if two terms occur together, if two terms occur with distance 1 in the document, right? If the terms are reversed with respect to the query and in the document. So all these kind of things you can actually incorporate in a standard, say, retrieval model, and that works very well. And skipping all that stuff, to kill you. Final slide on ranking. How does it work in practice? So I have the which. So I hope you see during the Learning to Rank lecture how this works in practice. But it's not very far away from the which in the cauldron. Essentially, you have all these signals. You have term frequency, document length, document fields. You have linkage information. You have information about the intent. You classify queries, for instance. You know what the user is looking for. If you're looking for news or products, or he's doing a transactional query or an applicational query. You have editorial information. You have geo information, language information, user preferences. You have a lot of sources of information. You use all these sources of information and you mix them in a machine learning framework. And this is what learning to rank is. Don't let Yi fool you into that learning to rank is something more complicated. Learning to rank, machine learning is just a way to efficiently combine all these features. Okay, that's it. And arguably even machine learning or pattern recognition is that. Right now a bit late. I'm just going to mention a few topics that of course I didn't cover, but I find really interesting. One is dictionaries. Have this index structure, how you represent the terms, especially if you want to provide auto-correction capabilities, for instance. Or you want to provide prefix query. You want to search for anything that has how star. Right? You want documents that contain houses, house, household, whatever. So there are interesting data structures from the algorithmic field that deal with these kind of problems. Hardware, know your hardware. That's very important because it sort of constrains anything else you can talk. Even had a slide on map reviews. Hopefully, you can get to learn about map reviews somewhere else. This is very important, very trendy right now. As I said, it sort of originated by the problem of trying to invert the document collection. There was distributed IR, caching, we talked a bit, and there's all this other stuff that is, interesting topics in the information retrieval field. Efficiency, how to do compression efficiently, how to store stuff, how to do caching and distribution. Novelty, how to surface things that are new for the user. Diversity, how not to cover the same topic over and over again. Just this Apple example, maybe your first result you want it to be about the fruit, but then the second result you want it to be about the computer. Evaluation, that I leave up to George completely. Relevance feedback. If users are actually telling you, this is wrong, give me more of this. How you incorporate that into the model, learning to rank, that info as well. How to model user profiles and user actions. We're really far away in this respect, I think, so far. We have a lot to learn. Sponsor search, how to surface the best ads for somebody. And then temporal aspects. So we didn't talk about this, how dynamic all this stuff is, but when you put in the dynamics, the whole game changes, and it's a complete different story, and very interesting as well. And maybe even social aspects. How does it influence that I know what your friends like, or if it should affect search or not? So all these issues are still open, and there's active research in each one of them. So hopefully I've made some of you interested into looking some of this up sometime. And I'm through. We went to 200 slides. There you go. Yeah. Thanks for staying this long. Any quick questions, or you want to rush? I can't see you, so you got to speak up. I'm blind. Yeah. Yeah. So you learn a lot about that on Saturday morning on George's presentation. I completely skipped that topic. It's a big issue in information retrieval. How you do evaluation, how you decide one thing or the other. Right. Anyway, I'll be around here all the week. Just feel free to grab me and ask me some questions whenever you want. Thank you.